तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Towards the end of the last lecture, we were talking about design of experiments, and lecture 7 on mechanical measurements, which is the current lecture, will also look at the design of experiments in somewhat greater detail. There are some basic ideas which we would like to understand, and also basic terminology which is used, which should be made clear before we proceed with some of the details. If you look at the first slide, what we are going to cover in this lecture is to talk in the general about design of experiments, some basic ideas involved in the design of experiments, which of course depends on the type of experiment, the type of measurement we are interested in, what is the end purpose of the measurement. So that to some extent or to a great extent actually determines what are the details we have to understand. Then we will talk about a class of measurements which is termed as factorial design, and we will explain all the terms which are used with respect to factorial design, and then we will follow it up with a simple example which I call it example 7, and then I will move on to the fractional factorial design. The difference between the factorial and the fractional factorial design is to reduce the number of experiments that need to be conducted, and that is to be done by using some basic principles, and that is what is going to be covered in this lecture. So the first thing we are going to do is to look at the definitions of various quantities, which automatically become important when we decide to discuss design of experiments. What are these? So the terms which we will meet with, we call it factors, number 1. Then we talk about levels, and then we will talk about replication. These are 3 important things, and let us see what they mean. Factors are those quantities that are going to be important because they are going to affect the outcome of an experiment. Whatever may be the nature of the experiment, there will be some quantities or parameters or some variables which are going to play a role in determining the outcome of the experiment. So what are these factors? So we call them factors, and of course all factors need not be equally important. Some factors may have dominant effect, some of them may not have that much of an effect, and so on. So in order to recognize the relative importance of the various factors, we have to conduct experiments. So that will become clear as we proceed with the discussion on design of experiments. The levels. So we talked about the factors. There may be n number of factors. For example, in a particular case, there may be, in the case of the example I took in the last lecture, you have a machining process, and the speed of the machine and the depth of cut were the 2 factors. So they will be recognized as the 2 factors, and the outcome of that experiment is of course the surface finish of the product, which can be given in terms of some numerical index. So the levels we are talking about here is what are the levels or the values the factors will take in the experiment. I may have a lower limit for the factor, and I may have a higher limit for the factor, and in conducting an experiment I may set these at different values. Okay? So the each value which I am going to use between the maximum and the minimum becomes a level. For example, the speed may be varied from a low value of let us say 1000 rpm to a higher value of let us say 3000 rpm in terms of revolutions per minute. I may choose one or two values in between these two limits, and therefore, the number of levels will be automatically equal to the number of values I am going to choose. The lowest, maybe 2 or 3 values in between, and the highest. So, you can have, for example, 5 levels. In another experiment, I may have only 2 levels. The one is the smallest value, one is the highest value. I just want to see how sensitive is the process to the level of this variable or the factor. So, the levels refer to the values the factors are given in conducting a certain experiment. So, these two are very important, and in the design of experiments we will see that these are going to play a significant role. The third aspect is replication or repeating the measurement. For example, here I have written refers to gathering of results repeatedly for a fixed set of levels for all the factors. In fact, I talked about 2 factors here, the speed and the depth of cut. With a given speed and a given depth of cut, I will repeat the experiment again and again with different stock or different material, or same material I may have different specimens, and I am going to vary the speed and vary the depth of cut. But in particular experiment, I am going to keep these 2 values at fixed levels, and at that those fixed levels I am going to repeat the experiment again and again. The replication is necessary to address the concerns regarding repeatability and also the spread or the variation in the outcome of the experiment. So, this is basically replication is to get statistical information about the process that is being modeled or being studied. So, the questions we are going to ask when we have identified a certain process or a certain experiment we have in mind, and before we conduct the experiments, we must find out what are the factors which play a role, and in fact, some of these factors may be important in their own right, may play a role independently. That means some factors may have independent effect on the outcome of the experiment. Some of them may also interact amongst each other. For example, the depth of cut and the speed may interact. That means that the 2 values may decide the outcome of the experiment, not only independently, but their interplay. That means we can, in other words, we can think in terms of some independent factors. That means that the outcome of the experiment is directly dependent only on that effect. For example, if I were to conduct an experiment with different values of one factor while fixing the other factor at a fixed value, I will be able, if the effect is independent of the factor which is fixed, then I should get the same values. The independent effect should be only manifested because of the variation in the value of the level of the factor which I am varying. However, sometimes more than one factor will interact with each other, and there may be different types of interactions, and we will look at this later. These interaction effects are more difficult to bring out, and the design of experiment basically is to find out what are the independent effects, what are the interacting effects, and what are the how we can quantify these effects on the outcome of the experiment. So, the question rightly will be, how do we find this, whether the factor is independent or there is interaction. In fact, sometimes we also call the important factors as main factors, and the interactions sometimes may be classified as less important factors. The more important factor is the direct involvement of the independent factor or the main factor, and the interactions may play a lower role. In fact, we expect in many cases purely from the knowledge of what is going on, that the interacting effects may be less significant than the main effects. So, there will be an hierarchy of effects, the independent effects or the main effects, and then the interacting effects which will have a lesser influence on the outcome of the experiment. There are several ways of designing an experiment or a set of experiments. So, one is of course a very simple design. It is simply called the simple design, in which what I do is, if I have several factors which can vary in an experiment, I will vary one at a time vary only one factor at a time, keep all others fixed at some values. I will come back to this simple design later when we talk about some difficult experiments where it may be necessary to do that. So, vary one factor at a time, and many times when we do this, we assume that factors do not interact. This information about whether they interact or not has to come from some independent experiment or some independent argument or some theoretical consideration. The only problem with this simple design is that a very large number of experiments are needed to get any significant amount of information about what is happening. So, the simple design is avoided most of the time, but there are cases where there is no alternative but to go for a simple design. So, we will come back to this simple design a little later on. Okay, let us look at the next way of doing it. We want to study the effect of each of the factors on the outcome of the experiment, and we can use what is called the full factorial design. Factorial here stands for all the factors being taken into account in running the experiments and then trying to get the information regarding the effect these various factors have on the outcome of the experiment. So, if I look at the full factorial design, what it tries to do is to test every combination of factor levels. Suppose I have 5 levels for a factor, all the 5 levels I will conduct the experiments. For each value of these, I will also have all the levels for all the other factors that are going to be playing a role in the particular experiment. The disadvantage of full factorial design is of course that a large number of experiments are needed again, but the advantage of this is that all interactions are going to be captured. We will explain this of course with a simple example. Example 7, I am going to work it out on the board. It will become clear as to what we are talking about. So, the advantage of a full factorial design is that it is going to give you information about all the parameters or all the factors which are going to decide the outcome of the experiment. So, let us get on with the idea of full factorial design, and let us explain the basic things about full factorial design, and I will work out the simplest example which will be consisting of 2 factors and 2 levels. But this is like a representative case. Once we understand how 2 factors and 2 level experiment works, it is easily possible to extend the arguments to generalize for any number of factors, any number of levels. Therefore, whatever basic information is required for the design of experiment is already present totally in a 2 factor 2 level experiment. So, let us look at the way we are going to go about. So, we have 2 factors. This is the example I am taking. I will take a specific example where I will indicate what the factors are as we go along. We have 2 levels. So, factor 1, for example, let us say factor 1 or factor A if you want, there is a factor B. The example we considered in the last lecture, factor A would be the speed of the machine, factor B would be the depth of cut in the experiment in which machining was the process which was being modeled. 2 levels I can have a high value and a low value, because 2 levels means there are only 2 levels. It is allowed to take only 2 values as far as this particular design is concerned. Again a high value here, a low value here. Normally what we do is we take the high value as +1, low value is -1, similarly here +1 and -1. It is very convenient to work with such numbers, and in fact you can also see the mean of these two is actually 0. The mean of these two is 0 as it is written. One is on the +1 side is the higher value, the lower value is -1, and the in between we have the 0 value. And we are not going to conduct the experiment here. What we are doing is only two levels, the high level and the low level are the two factors. In fact, I can factor A I represent by x subscript A, and factor B I will represent as x subscript B. And in general what we are trying to do is y is the outcome of the experiment is a function of x A x B. This is the general expression. Exactly what kind of function relationship we are going to have, how to do that, we will take it up as we go along. So if you look at the levels, I got a plus value and a minus value, and what I will do is I will indicate it in the next slide in the form of a matrix which is easy to manipulate. So I will say x A, I am going to have -1, +1, x B, I am going to have -1, +1. Now you can immediately see that the number of experiments I can perform is I can have -1 and +1, -1 here and +1 for x B. I can have -1 and -1 both low values for x A and x B. So we will just write it in words, both low, then we can have A low, B high, and then we can have A high, B low, and both high. So the number of experiments is easily seen to be 2 squared equal to 4. So we are now able to understand what is going on. We are conducting an experiment, and if I go back to the previous page, I have two factors, two levels. I am taking the two levels as the highest and the lowest value or high and low value in the experiment. So factor A, I will call it x A, is the numerical value or the identifying value for that. High and low I am going to use the values +1 and -1. Factor B, high value and low value again +1 and -1, and we are looking at the outcome of the experiment is y, and it depends on both the x A, x B. And as I was explaining earlier, it may be directly x A, x B, main effects, they are called the main effects, or it could be through cross effects. That means the x A, x B, product of x A and x B can also influence the outcome of the experiment. Therefore, we have 3 x A, x B, and the product x A, x B. These are the 3 effects we are going to be interested in. So let us look at the matrix we have written here. So I said that we can have -1 +1 for x A and -1 and +1 for x B. Therefore, if I do the experiment, I can have both low, one of them low, the other high, and vice versa, and then both high, and that represents number of experiments equal to 4. So let us look at this in slightly more detail. So, I will just write down all the experiments we are going to conduct in the form of another matrix. So, I will write here experiments and the factor level combinations. I will put it in the form of columns in a matrix again. So, I will say x a in x b. I will also include the product x a x b here, because we will see later that is also going to be an important thing as far as the effect on the outcome of the experiment is concerned. And we have, if you remember, we had +1, -1 as the high and low values. I will simply put them as plus and minus. The numerical value is 1, either it is plus or -1, and therefore, to be economical in writing, because we understand what we are doing now, I will just say plus and minus for these values. For example, I can take x a negative, x b positive. That means this is -1, this is +1. This low value, this high value. I can take plus here, minus here. I can take minus here, minus here. I can take both positive. So, the x a x b will be simply the product of these two. Minus into plus is minus, plus into minus is also minus, minus into minus is plus, and plus into plus is plus. So, what do we gather from this representation? If you look at this, we can look at each column as a vector, each column as a vector. We have minus, plus, minus, plus. When this is minus, this is positive. This is positive, this is minus. This is minus. These two vectors are linearly independent. They are independent of each other, because if I take the product of these two, which is what x a x b is, if you take the product of these two columns, that means that I am going to take x a x b and I am going to multiply the particular component. So, suppose I look at these as the 4 components of this vector, and these are the other 4 components of this vector. I am going to just multiply the components and put it here. You see that if I add this column, it is going to give you 0. So, sum, if I write, equal to 0 for this column. In fact, it is also 0 here and it is also 0 here. So, the property of this particular matrix is that the column sums are all equal to 0. However, if I were to square each one of these components, so you take the square of this, square of this, square of this and square of this, add, you will get a sum equal to 4. So, sigma x a squared 1 to 4 equal to 4. So, the sum of the squares of these is equal to 4. I think I will write it in the next pane. So, what I am doing is this: sigma x a 1 to 4 equal to sigma x b x a x b equal to 0. The column sums are going to be 0, because they are equal number of times they are positive, equal number of times negative. So, they just add up to 0. However, if I take sigma x a squared, this will be equal to 4 sigma x b squared. So, just to explain what I am trying to do, I am just trying to understand the idea of understanding the basic properties of these coefficients which I am using for the measurement process, because this is going to play an important role in the way we are going to interpret the result of the experiment. Okay. So, now let us look at the relationship between y and x a and x b and maybe the product x a x b. This can have up to 4 parameters. Why is it so? Because I am conducting 4 experiments, I have got 4 y values and the corresponding values of the x a, x b and the product x a, x b. Therefore, I will be able to fit a curve or find a relationship which can support only 4 parameters. Therefore, I will think in terms of what is that function which can have 4 parameters. I will take the simplest I can think of will be a linear relationship. So, I will say y equal to, the first one will be of course a constant, because the value of y can have a value independent of these parameters, that is is equal to, in fact we will show later that there is the mean value p naught plus p 1 or p a x a plus p b x b plus I will say p a b x a x b. This is the relationship between y and the parameters x a, x b and the interaction parameter. X a, x b is nothing but the interaction between the 2 factors. That means, when I have only 4 experiments, 2 parameters and 2 levels, 4 experiments I perform, this is all I can do. I cannot have any other relationship between y and the quantity x a, x b and the product of x a, x b. So, how do I find out these values? If I find out the outcome of the experiment with the different, there are 4 experiments I am conducting. In each experiment I know what is the outcome of the experiment y. So, now I will have 4 values and I will substitute those 4 values here and I will find out what is the corresponding values of x's in the right hand side, and then I will get 4 equations. So, 4 equations, 4 unknowns, p naught, p a, p b and p a b, and therefore, I will be able to determine these 4 constants from these 4 experiments. So, for doing that I will take a simple example which will clarify, because I am going to use some numbers, and therefore, let me take an example which was also mentioned in the last lecture, the same machining example. I have the surface finish. I am just taking one example which is familiar to us as mechanical engineers. You can take any number of examples are possible. Surface finish will be represented by y. The speed of the machine, I will represent by x subscript a, and the depth of cut as xp. In real machining process there may be many other parameters which may play a role, but we have taken a very simple one where we have ignored any other parameters or factors coming in the picture. We have only 2 factors. So, these are the 2 factors, speed of machine and the depth of cut, and the outcome is the surface finish. That means, the assumption is that if I vary the speed of machine or depth of cut, the surface finish must depend on the 2 values which I choose for this. Again, I can identify high value and low value. For example, the speed of the machine may be 200 rpm or 2000 rpm and 4000 rpm arbitrarily. So, one of them will be -1, the other will be +1. So, we do not have to worry about the actual number. One of them is given -1, the other one is +1. You can always transform the coordinates such that these 2 values you get. Depth of cut, it may be 10th of a millimeter it may be 0.25 millimeter. So, you can have two upper limit and lower limit, and those will become -1 and +1 respectively. Okay, depth of cut. So, surface finish I am going to measure using some instrument. This is measured after the machining process is done. We are going to conduct the experiment by machining the part. After the machining I am going to take it out and measure the surface finish using some instrument, and I want to link the value of y to the value of x a and x b which were used in the experiment. So, the measured values of the surface finish may be given some values. For example, I have taken something like 1 to 10. So, this is 1 to 10. In that scale I am going to fit in the value someplace by some formula. I do not have to worry about the details now. It is just to indicate how the example is worked out. This is example 7, that is what we started with. So, I am going to look at the surface finish, speed of machine, depth of cut, and make a tabulation of the results of the experiment. So, the results of the experiments are tabulated in the following way. So, I have -1, +1, or in the terminology I am going to just say -1, -10 plus for the speed of the machine. This is x a. I am going to write x b here, minus and plus, and the surface finish obtained is given in the form of a table with 4 entries, and the values I have obtained are 2, 8.2, 1.5 and 3.5 in this. This is the actual example. This is the outcome of the 4 experiments, of the 2 squared experiments. So, the outcome of the 2 squared experiments are 4 experiments, minus plus, minus plus. These are the values of the factors, these are the levels, and then these are the values 2, 8.2, 1.5, 3.5. Of course, this table itself immediately tells me that somewhere here I have a likelihood of getting good finish, because the outcome of the experiment is the surface finish, and in my terminology 10 would be a very good value for the surface finish, 1 would be very poor value for the surface finish. So, I am talking in terms of some relationship between the numerical value and the surface finish or the quality. So, now I will write the 4 equations using the model which we have proposed. So, if you remember, y equal to, I will just write the model here, P naught plus P a x a plus P b x b plus P a b x a x b. So, I will go into, there are 4 values in the table, and each one of them I can write the corresponding equation here. So, if I want to refer to it, I can just write here in capsule form. I have the 4 values, this is minus plus, minus plus, these are the 4 values 2, 8.2, I think 1.5 and 3.5. So, I am just going to see. So, this value, let us say 2, that is equal to 2 equal to P naught, both are minus. So, minus P a, minus means minus 1, minus P b, x a x b is 1, therefore, this becomes plus P a b. This corresponds to the first entry in the table. The next one, 1.5, P naught does not change, that is the constant. The value is minus P A plus P B. Now this becomes minus P A B, because the sub product of x A and x B is now minus into plus is minus equal to minus 1. The third one is I am going to have 8.2 . So, I want to write it a little bigger, so that you can easily see what is happening. 8.2 equal to P naught, that corresponds to this where the x A is plus 1, x B is minus 1, therefore, this becomes plus P A minus P B, again minus P A B. So, the lastly 3.5 equal to P naught, both are high. So, plus P A plus P B plus P A B. So, these are the 4 equations available to me to determine the 4 coefficients. And what are these coefficients? These are nothing but the coefficient which represent the effect of each one of the parameters. The larger the coefficient value, the larger the influence of the particular factor. So, if P A is dominant, P A is much larger than P B, or P A is greater than P B, then we will say that the parameter x A has a more important role to play in the measuring process than the parameter x B. Suppose P A B is very small, then we will say that the interaction between x A and x B is not very important. Okay. Some of the conclusions which we are going to draw regarding the nature of the effect of the factors is coming from these 4 equations. You will also notice that if I simply add these equations, all the other quantities will become 0, because P A minus P A minus P A, then there is a plus P A and plus P A. These 2 are going to cancel off with this, minus P B plus P B minus P B plus P B, they will cancel. Therefore, if you simply add these equations, suppose I call it 1, 2, 3, 4. So, the sum of the equations gives you the 4 P naught equal to 2 plus 1.5 plus 8.2 plus 3.5, and this gives a value of P naught equal to 3.8. That simply means that suppose the value of the x A and x B were taken to be the mean values. So, the high speed and the low speed, and we will take the intermediate value. Similarly, depth of cut, high depth of cut and low depth of cut, if I take the mean of these values, this is what I am going to get. Therefore, let us look at the interpretation of this result graphically in the next tablet here. So, I am going to draw a sketch of what is going on. So, I will say x A and x B, like they are coordinates along the 2 directions. So, this corresponds to plus plus, because both x A equal to plus 1, x B equal to plus 1. So, there is double plus or plus plus. If you want, you can put it a comma here. This corresponds to plus minus, this corresponds to minus minus, and this corresponds to minus plus, and this is the center of the thing. So, what we are trying to do is, suppose I had in some, because of some reason, I had assumed that this was the reference set I have a reference set for XA, XB. Then what I am trying to do is to find out what happens if I go to a value to the right or to the left, to the top, to the up or down. So, I am trying to study the effect of the parameters on how the reference value, which is nothing but P naught, is going to change. So, the experiment can be looked upon as a study of the process and the variation of in the process outcome when we vary the values of the two factors away from the mean value. So, it is like trying to understand what is going on in the process. So, this is a very physical way of explaining what is happening, and what I did in the previous tablet was just to give the same in the form of mathematical expressions. So, P naught I have already obtained 3.8, and the student can certainly obtain the other values, and I will just give the values in the subsequent next tablet. I can write it here. So, before we do that, let me just indicate how the solution has to be obtained. I think some details can be mentioned here. So, by adding 1, 2, 3, 4, the 4 equations I was able to get the average. Now, you notice that if suppose I want to find the value of P A, I have to make this plus. I have to make this plus, right. So, I will take minus of equation 1. So, minus 1, minus 2, 3, 4. What will happen if I do that? If I multiply by minus, this becomes minus 2, this becomes minus P naught, this becomes plus P A, this becomes plus P B, this becomes minus P A B. When I multiply this by minus, this becomes minus 1.5, this becomes minus P naught, this becomes plus P A, this becomes minus P B, this becomes plus P A B. And if you look at the column sums, excepting the column, this column, all other column sums will be 0 when I do this, when I add these things. Okay. In fact, the minus 1, this 3 minus 1, this is like 3 minus 1, 4 minus 2, right. Equation 3 minus equation 1 will involve, right, the difference between these two, and similarly 4 and 2, the difference between these two. These are referred to as contrasts. Okay. So, we take minus 1, minus 2, plus 3, plus 4, add to get P A. Then you can do the same thing with the next one. I have to make this plus and also this plus. So, minus 2, minus 1, plus 2, minus 3, plus 4, I get P V. So, you see that by very simple arithmetic operations, I am able to get all the values of the parameters. So, let me just give the parameters in the next tablet. So, the solution using the properties of the matrix are given by P naught. Of course, I already have given 3.8. So, P A works out to be 2.05. The student can verify these values by doing what I indicated, minus 1.3, and P A B, the interaction parameter, is given by minus 1.05. Now, I am going to ask myself the question, how do I interpret these results in terms of identifying what are the relative importance of the different factors on the outcome of the experiment. So, the question is, what is the relative importance of each factor? Each factor in terms of the main effect due to P A and P B and the interaction effect due to P A B. So, I have got 4 coefficients. One is of course the mean, And you see here, by having non-zero value for x a and x b, I am going to perturb this value from p naught equal to 3.8. Okay? So, the mean value is this. So, I can use the variance with respect to the mean as a measure of this effect. So, if I use the variance, I will tell you how to calculate the variance of the sample will be calculated as, I will call it as sy squared, the sample variance. This is given by sigma 1 to 4 y minus y bar whole squared divided by n minus 1. If you remember, we have 2 squared minus 1. Because we have already got p naught from these measurements, therefore, I have one less value, and therefore, I will use the formula n minus 1 in the denominator. N is 2 squared minus 1 is nothing but 1 over 3. Okay? And let us look at sigma yi minus y bar whole squared. I can take one of them and see what is happening. So, yi minus y bar is nothing but p naught. For example, if I take plus plus, that means that both high values, that will be p naught plus pa plus pb plus pab minus p naught, because that is the mean value. This is nothing but p naught plus pa plus pb. I am going to square this, okay, because I need the square of this quantity. So, you can see from the property we talked about earlier, the sum of the squares of the column are going to be 4. That is going to be important in this. In fact, if you do this, you will see that it is nothing but the square of this piece. They will add up to, the columns will add up to 4. Therefore, it is easy to find out what is going on. So, p naught is simply a coefficient, p naught multiplied by the column sums of the squares of the columns, okay? And sums of the squares of the columns are going to be 4, which we already showed how it happens. Therefore, we can say that sigma, I am going to leave it as an exercise for the student to figure out, divided by 3 will be nothing but 4 pa squared. I am sorry, I left out one thing here, plus PAB. So, 4 PA squared plus 4 PB squared plus 4 PAB squared divided by 3. So, the variance of the sample or sigma y squared, contribution is 4 by 3 PA squared, 4 by 3 PB squared and 4 by 3 PAB squared. Therefore, the coefficients are going to be giving an idea as to what is its role in the outcome of the experiment. What is its role in the outcome of the experiment? Now, I can put the values of PA, PB and PAB, which was determined in the last slide. So, what I can do is I can introduce this and I will just give the values. So, we can show that sigma y squared is equal to 5.6 plus 2.25 plus 1.47. And if you add all these things, you are going to get 9.32. So, this is going to be equal to 9.32. So, what I can do now is take the ratio of each one of these with respect to the total, and that will give you the percentage effect of the particular factor on the outcome of the experiment. Therefore, I can say A, B, AB, another way of writing the effect of these. Here I will say percentage effect. The effect is measured by the contribution to the variation. Variance is the variation which is because of the effect of that particular factor. So, we are looking at the contribution of each one of these. So, I will say 5.6 by 9.32 multiplied by 100, I will put it as a percent. This will be 60.1. Next one is 24.8 and the third one is 15.8. If you add all of them, you should of course get equal to 100. Sum is equal to 100. That means 60% of the variation in the outcome of the experiment is because of the speed of the machine. Therefore, speed has got a more important role to play in the process which we are talking about. The depth of cut has got an effect, but it is less than the effect of the speed, and the interaction between the two is not unimportant. It is also important in this case, but it is much lower than the effect of each one of the individuals. So, we will say these are the main effects. Main effects are 60 plus 24, 84.8%, and the interaction effect is about 15%. So, this is not necessarily ignorable or negligible in this particular case. Therefore, in this particular experiment or in this particular process, the speed, the depth of cut and the product of these two are all playing a significant role. However, the relative significance of each is determined by the relative magnitudes of the variances due to each one of these, and that is what we have tried to do there. So, let us get back to the slide in which we were looking at before we went to the tablet PC to write out the things. You will now appreciate that by doing the full factorial experiment, I am able to calculate all interactions. In this case, the interaction is only one interaction, XA multiplied by XB was the only interaction. If the number of factors becomes larger, the number of interactions also become larger, as we will see in a little while from now. So, let us look at what might happen if I do an experiment with a full factorial design. What will happen is that if the number of parameters or number of factors is large, the number of experiments needed to capture all the effects. In the previous case, I had only one interaction effect, XA product XB. In the case of many number of parameters, I will have many such combinations. I may have combination like XA XB, XB XC, like that. I may also have XA XB XC, product of three terms at a time. I may have XA XB XC XD, so 4 things taken at a time. So, there are large number of such effects may be important, or we may have to study them, and therefore, if we want to capture all these effects, the number of experiments to be performed becomes excessively large. For example, a 10 factor 2 level experiment requires 2 to the power of 10 or 1024 runs to bring out all the effects. In a laboratory experiment where we want to conduct these experiments, 1024 experiments are going to take months and months. If each experiment takes several hours, it is going to take a large amount of time and effort on the part of the experimenter. The question now is it possible to reduce the number without losing too much of the information? That means, we go for what is called a fractional factorial design. The idea of this fractional factorial design is to use not 2 to the power of 10 in the previous case, instead of that I will use 2 to the power of 10 minus 4, let us say. That means that I am not going to use all the 2 to the power of 10 experiments. I will choose from this 1024 experiments which are possible, I will choose the ones in a very careful manner, so that it will bring out the most important effects I am interested in. Because as you saw in the previous case, XA, XB are having more important role than the product XA, XB. So in general, if the number of parameters is large, the main effects will be due to each one of these factors, and the product or the product of 3 quantities taken at a time, 3 factors at a time, and so on, they may become less and less important. If it is found from some other study or somebody else has studied the problem before, or if we have some independent reason to believe that only certain interactions are important, why do you have to do all the experiments? You do only a certain number of experiments to bring out the important effects which we want to study, and that is what the fractional factorial design does. So the result is that we cannot resolve all the interactions very clear, but some of the interactions may be unimportant. Therefore, what we will do is we will try to find out whether we can run a fewer number of experiments and get whatever information we want. So this idea of fractional factorial design we will discuss in the next lecture, and also discuss the simple design which we talked about in very small minor detail in this lecture. We will try to continue with that in the next one. Thank you.